So good morning, everyone. Welcome to our webinar, How RISC-V will set you free. My name is Theo Tiemann. Today I will be the host of the webinar, and I'm a program manager in the high-tech and big science part of Technolution. I'm very pleased to introduce to you Gerard Rauwerda, and he is today's presenter or speaker. Okay, Gerard, a warm welcome, and please tell us more about RISC-V.
Okay, thank you, Theo. Let me introduce myself. My name is Gerard Rauwerda. I'm a business developer at Technolution and responsible for the big science and space domains. And it's actually my objective to bring science and technology together. So a brief outline of myself. I obtained a PhD degree in computer science on reconfigurable multi-core embedded systems. And I also hold a Master of Science degree in electrical engineering with a specialization in telecommunication systems. And actually, out of my PhD research, I co-founded the fabless semiconductor company Recore Systems. With Recore Systems, we developed scalable platform system-on-chip architectures and reconfigurable semiconductor IP. For instance, together with the European Space Agency, we developed fault-tolerant multi-core DSP architectures along ESA's next-generation DSP for space roadmap. And moreover, I've also been developing multi-core and many-core systems-on-chip architectures for software-defined radio applications and streaming data analytics applications. And so a little word about Technolution. Technolution is already in business since 1987. We are a technology integrator who creates high-end solutions that add value to the customer's products. And today we are with a team of about more than 220 colleagues who all have a passion about technology and who work on innovative products, systems, and technologies for a wide range of clients. We apply our broad knowledge on high-speed electronics, programmable logic, FPGA, and software in our solutions. And although we are a fully Dutch company, we also have operations next to the Netherlands, in Denmark, in Sweden, United Kingdom, and since recently in the United States. So today, we will talk about the RISC-V open standard collaboration. First, I will highlight the flexibility and the portability of the RISC-V instruction set architecture, and I will show what advantages this brings us for our own products, as well what advantages it brings our customers in their engineering projects and their products. We will touch why and how we apply RISC-V and high assurance NATO certified encryption devices, and we will also show the portability towards radiation hard FPGA technology for space. And then in the end, I hope that we will all conclude that there is a bright future for RISC-V ahead. What is actually RISC-V? With RISC-V, we could actually say that we have entered into a new era of processor innovation through open standard collaboration. RISC-V is free and it's an open instruction set architecture. And based on this open instruction set architecture, based on this standard, processor designers have the ingredients to build their own RISC-V compliant processors. The standard has defined default instructions. It has defined optional instructions, but it also leaves room to customize your own instructions. So to customize your own processors while they are still RISC-V compliant. And how did we came to this point? Therefore, in the next slide, which I kindly borrowed from the RISC-V Foundation, we will actually show you the history of processor innovation. Processor design started somewhere in the 80s with a couple of companies who defined their own processors and their own software, their own tools. The design was closed to others, but unless you paid high licensing costs, you could use the designs. And we also saw that the processor design actually started with complex instruction set architectures. So it was dominated by complex instructions. Then in the 90s, actually the performance of chipsets was increasing. As a effect of Moore's law, devices became obsolete sooner. So this actually means that the life cycle of devices became shorter. So more devices were developed, and there was also a more widespread, diverse use of chipsets. And then, of course, in 2000, let's call 2000 the mobile era, performance and power becomes more and more critical, which also logically means that you need to accelerate functions in hardware instead of software. We see that there are more applications becoming available, so applications become more diverse, and designers are also looking for alternatives to the closed architectures. So because for the closed architectures, designers need to pay high license costs, so there was a quest for open cores, freely available cores, or cores available at reduced license costs. And then in the 2000 era, also there is a diversity of open cores popping up. I specifically say diversity because there's no coordination. Everybody has his own open core. There's no ecosystem. And that's why we actually today, what you see today, there's still a lot of custom processor development because of diverse computing needs. And today, there's also a coordinated community to create, to share, and to reuse processor development IP. And this is actually what we would like to have. So to have a mature ecosystem where there is software available, where there is tools available, and where there are compliant processors available. And that's where we are nowadays. So there is a rich and vibrant RISC-V ecosystem, and I will tell you how this actually happened. In fact, Technolution is one of the first founding members of the RISC-V Foundation. And the founding members recognized the need for a community to coordinate and to boost the development of core technology. Also to stimulate sharing and to stimulate reusing of processor technology. And actually, to have a kind of Linux ecosystem, but then not for software, but for embedded hardware. What we now see is that starting with only 27 founding members, we now have a rich community of over 750 members, which happened to appear in 5 years' time. Once you are a RISC-V member, the RISC-V members can build RISC-V processor architectures of processors based on the RISC-V standard. But we also see there is a broad range of RISC-V compliant tools and software available. So there's a rich ecosystem. We may compare actually the RISC-V Foundation to what Linux did for software. For Linux, what you actually see is there are open source implementations of the software with community support, without community support, but there are also commercial closed implementations with commercial support. And this is also what's happening in the RISC-V community. So for RISC-V, this is similar. A RISC-V is an open standard, and the processor implementations are not necessarily open source. Technolution, for instance, built its own closed source implementation on which we can offer support to our customers. And I will show you later on why we decided to do so. First, let's focus on the trends in system-on-chip design. And the complexity of systems is increasing, and more functions are actually integrated into systems where each function in a system actually requires customized processing. So we see, the result is a heterogeneous system-on-chip design. And of course, still for the best power performance ratio, functions will be accelerated in hardware, where typically the control of the functions is handled in software running on a general purpose processor. So these so-called hybrid solutions. And then if we combine all this, typically for mixed criticality systems, small chunks of code or small individual functions are running on separate isolated cores. And in this way, you can create mixed criticality systems where the separation of concerns, so running small functions on tiny processors, contributes to secure, safe, and reliable systems design. Now, for Technolution, portability is also an important motivation to consider the RISC-V standard. At Technolution, we target reliable solutions that matter for our customers, and it also means that we develop technology agnostic solutions with a focus on multiple target FPGA platforms or even ASIC platforms. So we would like to prevent from vendor lock-in. For instance, you could also use the soft processor IPs, which are offered, for instance, by Intel or by Xilinx, such as the NIOS processor or the microblaze. And you can use that to run your control flow software. But from a lifecycle management perspective, we don't want to stick to one specific FPGA vendor. During the lifetime of a product, it might be better for instance, costs, availability, obsolescence, or volume considerations to migrate the product to another FPGA's device brand. So that also means that we know with our RISC-V processor implementation, we can always rely on the same processor. We can rely on the same compiler and on the same software. Something which is not possible if you stick to, for instance, microblaze or NIOS, and you need to migrate to another FPGA brand. So you need to migrate your code from microblaze to NIOS. And for qualified products, this really shows advantages, as we, after migration, still use the same processor, the same compiler, and the same software. So these are already qualified, so this eases qualification and certification of certain products. So in conclusion, RISC-V is an open standard with a standardized instruction set, and also with instruction set extensions. And moreover, the standard leaves also room to implement your custom instructions. And we have now seen that with more than 750 members, RISC-V embraces already a vibrant ecosystem with RISC-V compliant tools and software. The main reason for us is that it offers flexibility. Our implementation is technology agnostic, allowing easy portability on different platforms. And our implementation also offers full transparency, which is advantageous during verification, validation, and certification or qualification of your product. Okay, let me remind you that you can ask your questions via the questions pane. I will now continue how we apply.
Actually, Gerard, we do have a question. Question is, what would you mean that your company focus on portability of RISC-V for ASIC device?
What I would mean that we focus on portability for ASIC devices.
Yeah.
So we develop technology agnostic. So that means actually our designs can be implemented on every major FPGA brand. And since it's a full VHDL implementation, we could also migrate or port the same design towards ASIC technology. Of course, then you need other backend tools you need to synthesize for ASIC. But the design is technology agnostic. Everything is implemented in VHDL, so we could easily port the same hardware to an ASIC implementation.
Yeah, there's another question as well, but I suggest to answer that one at the end of the presentation. Please continue.
Okay, thank you. Okay, so taking into account all the considerations, we have implemented the so-called FreNox family of RISC-V processors. We have implemented a tiny 32-bit embedded processor, which is based on the default instruction set, including the multiplier extension. And we have an application processor available, which implements on top of the embedded processor atomic instructions, as well as the supervisor privilege mode. And that application core also comes with a cache implementation and memory management unit. And now I will show you that we are active in multiple market domains and where we apply our expertise on electronics design, programmable logic design, and software expertise, and also where we apply our RISC-V implementations and RISC-V expertise. So Technolution Advanced builds, for instance, high-speed data acquisition and control systems for semiconductor and life science equipment, like lithography machines, metrology machines, electron microscopes. And Technolution Prime builds actually state-of-the-art security solutions and also preventive high assurance solutions for classified data communication, so NATO certified solutions. And then with Technolution Perform, we built innovative solutions for industrial machines, so digitization of manufacturing machines, such as robotization, AI, computer vision. As I said, we built NATO classified secure line encryption products, and actually those devices follow the hybrid system model. We have control flow software, which is running on the RISC-V processor. And for our hardware VPN solution, there's of course also data encryption and data decryption between an untrusted and a trusted network. And this data encryption and decryption is implemented in hardware logic. Now you may wonder why to use RISC-V in this example. Actually, especially for this certified security product, we had full understanding of our custom RISC-V implementation. And the open standard also allowed the customer and the evaluators of the product to easily assess the implementation. And then from a lifecycle perspective, we believe that the transparency and the portability will pay off in the future, as there will be a period in time that we need to migrate the design to other FPGA devices. For instance, because of obsolescence of components. So the transparency of migrating will ease the qualification and the certification of this product. Now let's focus at another domain, reliable computing for space. We actually gained expertise with the European radiation-hardened FPGA technology from NanoExplore, a French company. And using this NanoExplore FPGA technology, we implemented the full system on chip based on the FreNox embedded processor. We have implemented that full system on chip in the FPGA, and we also demonstrated it in the radiation-hardened FPGA. And it's our belief that the space domain may also take benefit from RISC-V, as it offers, for instance, a mature software and tools ecosystem. And you have full transparency and full control over your hardware. So a little bit more detail about the full system on chip. I will not go into all the technical details. If you have any questions, we could do that afterwards or by a follow-up. This is just to show that we implemented the full system on chip, which includes the RISC-V core, So the FreNox-E here, it includes instruction memories, data memories. We have AXI4 bus logic implemented, and we have implemented peripherals such as interfaces and real-time clocks. We also have an implementation actually with SpaceWire RMAP implemented, but that's not shown in this presentation. And for all our programmable logic and embedded software projects, actually continuous integration is a common practice. Verification with simulation starts already early in the design cycles of a project. So before implementing the real FPGA platform, we already can verify a full application scenario in simulation. And with this full automated testing, with scripting, continuous integration, and nightly builds, we are able to offer quality to our customers. Our development process results in reliable, repeatable, and predictable solutions. If you would like to know more about our verification and validation strategy, I encourage you to watch our earlier webinar on shift-left tested FPGA designs. The link to this webinar will be provided in the follow-up email at the end of this webinar. So after having done the verification, of course, we validated the FreNox system on chip in the NanoExplore FPGA technology, so in the real hardware. And in that real setup, the emulated interfaces from the verification setup have actually been replaced by real USB interface bridges. So that means that the application that we already run in the verification environment, we can reuse the same application again and run it in the validation environment, where we only replace the emulated software interfaces with the real USB interfaces. Several integer and fixed point benchmarks have been implemented and run on the FreNox embedded processor. And those benchmarks actually show good performance for control flow applications. And then we also implemented the FreNox system on chip on different FPGA platforms. Some results are shown to give you an impression of the resource allocation and the complexity of the full system on chip. I can already say that about 60% of the FPGA resources was consumed by the FreNox core, and the other part was consumed for the bus interconnect and for the peripherals. So in summary, the RISC-V standard offers an instruction set architecture with default extensions, but it also leaves room for customization for custom instructions. And based on this free and open standard, based on this free and open standard, you can build your processor and you can have compatible tools and software. So what we already see is there is a mature and rich ecosystem with a lot of tools and a lot of software. So your applications can benefit already from proven software and from proven tools, which is a large benefit. Then also what we see is that the RISC-V instruction set allows application customization. So there's a lot of flexibility. And for us, it prevents us from vendor lock-in when we target technology agnostic solutions. Imagine, for instance, the benefits during lifecycle management when migrating your design to an FPGA, or, as the question already was, to an ASIC platform. Everything is transparent in this way. Everything is transparent in this way. Verification, validation, and certification always will rely on the same hardware and software code base. So if you migrate to another FPGA brand, to another platform, you can still rely on the same hardware code, on the same software code, on the same tools. So thank you all for your attention. I can imagine there are still some questions. I'd be glad to answer them.
And yes, we do have additional questions. We can run through them. One of the questions is, if I normally would have wanted to use an ARM processor on a Zinc FPGA, would there be any reason other than the portability for using RISC-V instead?
Okay, so the question is, if I have already an ARM processor available on the Zinc platform.
On the Zinc, yeah. Is
Right.
then portability the reason to use RISC-V?
That's of course it's a valid question, and it's also difficult to answer right now. It of course depends on the business case you have. For instance, if you would like to stick to a Zinc platform, to an Intel platform, and you can use that specific platform for your product, then it would be fine to use that platform for your product. But we know that certain products have a long lifetime, and you can also see that sometimes components become obsolete, and then you need to make choices. So you need to migrate your design to another platform. That might, for instance, be a newer Zinc platform, where there is another version of the ARM processor. So that also means that you need to have new tools. You need to port your software to the new processor architecture. And yeah, that can hurt in the end. So
Okay.
it's not a question of yes or no.
All right. Thank you. We do have some other questions. Do you also use VHDL for verification, or do you use another language like System Verilog, for instance?
Okay. Shall I go back to the slide of verification? I think it's good.
Yeah, I also do have two other questions.
So we now see the verification and validation methodology. Actually, what we develop VHDL platforms, and we use the environment CocoTB, which is an open framework, which are Python coroutines to support the verification. So we have a full VHDL implementation of our hardware platform, and we use high-level Python coroutines and Python scripts to help to support the verification. So there's no involvement of System C or System Verilog. It's the combination of VHDL and the Python coroutine environment from CocoTB.
Okay.
This will also be explained in the webinar, the shift left tested FPGA design webinar.
Yeah, which we will include a link of in the reply email. There's a question about the implementation of our RISC-V IP core on the NanoExplorer SoC. Did you observe any difference in the single event failure interrupt occurrence between a NanoExplorer IP processor and your RISC-V core?
I cannot answer that question right now because we did not do any fault insertion tests, etc. So we migrated the design to the NanoExplorer technology. We observed that the processor is performing. It's running software. We actually can show a full demo, which we hope to release in a couple of weeks from now. So there might be an upcoming presentation about RISC-V in a NanoExplorer technology. including a demo. But we did not do any fault injection campaigns, so I cannot answer that question right now.
All right. And then the last one, does your design support floating point operation? The circuit area seems impressive if floating point unit available.
No. So we implemented the I instruction set, so the fixed point and integer instruction set, including the multipliers. The floating point extensions have not been implemented, and that's mainly because for the applications we currently target and the control flow we currently target, we actually see that the 32-bit fixed point and integer is sufficient for our applications. If there is an application which should need floating point, then we can of course always consider to add floating point, the floating point extensions to this architecture.
All right. Well, thank you for answering the questions, Gerard, and keeping an eye on the time. We have to close our session of today. Gerard, thank you for a very interesting and informative presentation, and also thanks to the participants, of course, for sharing your time with us. If you still have any questions later on, please contact Gerard or myself, and you can do that through the details which are shown now on the last presentation slide. Thank you for your attention.